everybody. Welcome to the first lesson for Module 6. Module 6, which we're going to be in for a couple weeks, is on correlation and regression. This is a topic that we could spend an entire semester on, so we're only going to scratch the surface of what we could be doing. So we're going to start with correlation. Correlation examines the relationship between pairs of numeric variables. For example, the one we're going to look at in our example today is the relationship between population density and property crime rate in Charlotte neighborhoods. So using that quality of life data set that we've been working with. So before we do anything else, anytime you run a correlation, you first want to get a visual of the data. So you want to see a scatter plot. So to look at a scatter plot in SPSS, we're going to do graphs, legacy dialogues, scatter dot, and we're going to pick simple scatter and click define. And we're going to take one variable and put it on the x-axis, one variable on the y. For correlation, it doesn't really matter which one is which because there's not really an independent variable and a dependent variable. But when we talk about regression, there is. So let's, we might as well go ahead and put what's going to be the independent variable on the x-axis. So between population density and property crime rate, I think we'd be interested in seeing how population density predicts crime rate. So we'd want to see population density on our x-axis and property crime rate on our y. Okay, and you can go in here and mess with titles and whatnot if you want to. There's some options, but I don't think we want any of those. So we'll click OK, and we get our scatter plot eventually. In the meantime, I'll show you that they do have this chart builder, which I've not really played with. This, I think, is what they want people to use going forward, but it looks a little bit more complicated than just using the scatter dot. All right, so I've copied this over here. This is our scatter plot. I think we can see it definitely doesn't look like there's a linear relationship. There's a couple of outliers here. I'm not sure what this one is, but I did look up to see what this variable is. This is uptown, where the population density is actually low because there aren't that many people who live there, and only the people who have residences there are considered part of or go into that calculation. So they actually, if you look at how many people are there, it would be a high density, but so that's why low density, but you can imagine there's a lot more, pickpockets and whatever going on uptown. So otherwise, we really don't see a linear relationship. Other than these two, those two make it look like it might be a nonlinear relationship. But we'll proceed with this anyway, just as an example. So before we get into the correlation calculations, I wanted to give you a little bit of insight into how that calculation works. And to do that, we first need to look at the sample variance and the sample covariance. Now, we've seen sample variance before, but just to refresh your memory, the sample variance is a way of looking at how much variability there is in X, in a single variable. So we're looking at all of the distances between X and the mean of the x's. And then we're taking the sum of those square terms and dividing by the number of observations minus 1. Okay, so that's the way of looking at the amount of variability within X. Well, the sample covariance, we're looking at the amount of variability between X and Y. So instead of X minus X bar times X minus X bar, we're doing X minus its mean times Y minus its mean, and then dividing by the sample size minus 1. So this is a way for us to look at how much variability there is between two variables, okay? And you see that the variance is basically the same as the covariance, except it's X with itself rather than X with Y. Okay, and I tell you that not because I expect you to be able to do the calculations, but because I want you to understand how they work. So if we look at the way the sample correlation is calculated, it's the covariance. So again, that's the amount of variability between two variables, X and Y. And we're essentially scaling it by dividing by the standard deviation of the X variable and the standard deviation for the Y variable. So this is the variability, but scaled so that it's on a scale between -1 to 1. All right, and this describes both the strength and the direction of any linear association that would exist between those two variables. So the sample correlation is R. Population correlation is this Greek letter rho, which looks like a P, but it's actually a Greek letter rho. And interpretation of this is any negative correlation means that there's a positive slope in the graph. So as one variable increases, so does the other one. A negative correlation is a negative slope. So as one variable increases, the other one decreases. And then if we have a correlation of 0, it means we really don't have a predictable relationship. So as one variable increases, the other one could kind of go either way. So that's the direction. Now let's talk about the strength, okay? Because correlation looks at both strength and direction. So in general, correlation is on a scale from -1 to 1. And the closer you get to the to -1 and 1, the stronger the correlation is. Okay, and correlations that are closer to 0 are weaker. So different people have come up with different, kind of guidelines for what's considered to be strong or weak or whatever. This is just one set of guidelines. You may see different ones different places. But in general, I want you to know that this is on a scale. These are not set in stone. And just like every effect size we've seen this semester, you should always compare to similar studies as opposed to, comparing to these guidelines, which are somewhat arbitrary. But what's important is that you know that closer to -1 and closer to 1, those are strong relationships. Closer to 0 is a weaker relationship. And you should know what negative, positive, and 0 indicate. That a negative relationship means that as one increases, the other one decreases. A positive one indicates that they both increase together. And a relationship of 0 means that as X increases, Y is just not predictable. So just to give you a little bit of intuition about what a scatter plot for various correlation coefficients would look like, I just created a bunch so that you could see all of these are positive, so they're easier to compare. This is a perfect relationship. This is actually called deterministic, when you've got a relationship where the correlation is exactly 1 or -1. So this is perfectly linear. This is not if you've got a situation where the data is deterministic, that's more of a situation where you deal with algebra or calculus or whatever, as opposed to statistics. Because there's no, there would be nothing really to infer. So this one is a very strong correlation. You can see a straight line would fit through there very easily. But it's not perfect. It's just very close. And then you can see as this goes on, you get weaker relationships. You can still see for both of these where the line would go, where a straight line would go. But the points aren't clustered as closely to the line. In R of 0.062, you really just can't even see the line, a line that goes between them anymore. So this is practically 0. This is very, very close to 0. And then I also wanted to show you an example of one where these points clearly have a relationship to each other, but it's just not a linear relationship. And so when you have that situation, you're not going to see the relationship reflected in the correlation. So the correlation coefficient cannot catch nonlinear relationships. To calculate this in SPSS, you just have to go to Analyze, Correlate, Bivariate, and then we're looking at population density and property crime rate. So we're going to move those two variables over, and it doesn't matter which one's listed on top. And then everything else you can just leave the same and click OK. So this gives us our output. So I've copied this over here, and our correlation, our sample correlation is showing up right here. So this is negative 0.062. So you can see that's a weak correlation. It's negative. So as one increases, the other one decreases, but that's such a weak relationship that it's hard to even talk about it being negative. And you know this is the correlation because it says here's the Pearson correlation, and you're looking at the intersection between population density and property crime rate. This is shown like this because you're able to put as many variables on there at a time as you want to. In fact, let me show you what you could do. So if you wanted to add more, just pick a whole bunch of them. You can click OK, and you can see a ton of correlations there at one time. But every one of them is going to be on there twice. So property crime rate and population density is here, but it's also here underneath this diagonal. So you're only going to be looking at the ones that are above the diagonal. So there is a hypothesis test for correlation. We're going to assume that the population correlation is 0. In other words, that the variables are not linearly related, unless or until we have enough evidence to say otherwise. So our alternative hypothesis is that the correlation is anything else, anything but 0, because that would indicate that there is some sort of linear relationship. The assumptions for the correlation test, there are 4 of them, and we don't have to really talk about the first 2. You don't have to talk about the first 2, especially in your write-up, because we're not going to run a correlation unless we've got variables that are numeric, where the observations are paired. And when we say the observations are paired, we just mean that, let's look back up at our scatter plot. That just means that, each dot here represents the same neighborhood on population density as it does on property crime rate. Okay, so we don't have those out of alignment. We don't have population density for one neighborhood and then property crime rate listed with it for a different neighborhood. And then there are no outliers. We have violated that assumption with our data. And so we might ought to consider removing Uptown, because Uptown is, I consider that to be a different phenomenon. So it's not really comparable. So we should probably take that out. I haven't done that here, but we should. And that our relationship isn't non-linear. And that's another one of those. You're probably not going to even run correlation if you see that you've got a situation like this one up here. All right. Now, to get our p-value and our, well, we don't have the test statistic, but to get our p-value for the correlation test, it's the sig two-tailed here, right underneath the correlation coefficient. So this is the p-value on the correlation test. Which is 0.198. Okay. And we do have an effect size for this, but we've already talked about it. The effect size is the correlation. So a sample write-up is that we ran a correlation test. So as usual, that's our first sentence saying what we did. And then we talk about our descriptive statistics, which is the same as the effect size here. So the sample correlation was negative 0.062, which tells us that there's very weak relationship. And the correlation did not differ significantly from 0. We state our p, which really tells us that there's not a meaningful relationship between these two variables. All right, so that's it, and we'll talk about this more in class, and in the meantime, if you have any questions, let me know.